Hi everybody, welcome back. So I have a medium to long term project of modeling a Fender Twin Reverb amplifier. Wanted to talk a little bit about uh, my progress, particularly with modeling the Tonestack EQ. So this is the circuit for the Fender Twin Reverb. It's two almost identical input stages with triodes, Class A amp circuits, and then this right here is the Tonestack. So we can zoom in a little bit. We have our three capacitors and a couple potentiometers for the treble, mid, and bass, and then that kind of gets buffered and reamplified by this additional triode before heading off into the power amp section. So and it's pretty much identical. I should be identical for the vibrato and the normal channel of the amp. So why focus on the Tonestack? Well, I mentioned this on my coffee page. If you haven't watched Jim Lil's videos, I highly recommend this one. And his findings are, I agree with them. The majority of the guitar amp tone comes from the EQ, and then also the speaker and cabinet at the end. So I haven't got to the cabinet simulations yet, but that can just be done with impulse responses. There's nothing particularly special there, just getting some good IRs. But the EQ is a little bit tricky. Now, if you followed me for any length of time, you know that I've harped on about how any sort of DAW EQ can model any other EQ, and there's not really anything special about these analog EQs. And what I mean by that is that you can get the same curve with any sort of second order EQ. Like in Ableton, it would be EQ8, but Logic has its own EQ. You can get those curves. You might need a few more bands. And one thing that does change is the sort of the response to the controls. So here, this website is very helpful. Shows you just what that Tonestack circuit is, but only the Tonestack, and lays it out a little bit neater. So you can see just by dialing in these controls, sometimes it's affecting, depending on what you're doing, more than just the one band. And the reason for that, see, there you go. You can see the other bands are sort of dependent and coupled with that control. And the reason for that is because you can see these potentiometers here. These are all just passive components. You have your capacitors and your resistors making up the RC network, but there's no buffers between them. Some EQ circuits, they have op amps or transistors to buffer the different bands, but for these guitar amp circuits and some passive studio EQs like a Pultec, for instance, you just have the sort of floating bands where they're coupled with the other bands. So that results in sort of two things. First of all, you get higher than second order circuits. In this case, you get a third order circuit. And additionally, like I said, if you move one parameter, it might sort of change the other bands as well. So I think it's worthwhile to try to model this correctly, which I have done now, actually. Foreshadowing, I'm making this after I sort of figured things out. Yeah, you can really see the character of the bass band change as you're going out of the range here. Um, this is the TMB with the parameters matched here with what the Fender Twin Reverb would have. I think the only thing I had to change was just RN needs to be 100 kilo ohms, and it was, I think, 47 kilo ohms by default. So changing that gets you the response, and you can check the values from the schematics, of course. So Karma, as in the school in California for audio processing, has done a couple papers, and here's one of the papers by David Ye and Julius O. Smith, who are heavyweights in the DSP world. This is a good read. They did an analysis of the Fender Bassman circuit, so it's not exactly the same. The only difference, the only real difference is that actually we can pull it up here. This is a potentiometer with the midband sort of being split, and of course some different values, whereas on the Twin Reverb circuit, this is it's, instead of being sort of a voltage divider in the potentiometer, you have just a variable resistor configuration with the wiper tied to this terminal. So it does change the response, and it does change the equations, but if you're looking for an easy implementation, this paper already lays out all the coefficients and then discretizing them with a bilinear transform. I believe they use Mathematica, which has proprietary software and a little bit expensive. So I wanted to do sort of the same thing with open source toolchain, aside from Max itself. But it can be done. So just before I jump in, there's also this slide deck from the guys at Karma, the same authors as the paper, and this is a little between the two, between the paper and this, they're very helpful in determining what needs to be done and just serving as a reference. So I'll be pulling this up as we're going along. I guess the first thing of note is actually, I'm just going to open up that paper again. The first thing of note is that there's a lot of different types of digital filter topographies, and this form, so this third order system with the conversions they have, is the Transposed Direct Form II. So that is important. I'll show you what that means here. But if you're using their formula for the discretization of the variables, then you'll have to use this form of digital ladder filter. So the Transposed Direct Form II is this one, where you have your X. Let me just make sure this is, that's this one. So you have your X coming in, your B coefficients, and then there's one sample delay, one is getting added, 1 second sample delay getting added, and then we're taking this feedback back through with another coefficient and another coefficient. So this is the second order diagram, but to make it third order, you just extend this down. You'd have another term here, B2, and another negative A3, or sorry, B3 and A3, and one more single sample delay. So let's take a look at the circuit, and I just implemented this in this handy little program called QSAPIC NG. I think it maybe is based around NG Spice. But you can draw up your circuit. It leaves everything in terms of symbolic variables, and if you're careful with how you're naming them, for instance, this one I named 1 minus t times RT. That's gonna work really nicely when you make your expressions. So this this tool kind of it's used to get a Laplace domain, which is continuous time domain transfer function. So that's your output over your input. I'll show you in the paper if you haven't come across this before. It's quite helpful to know. But yeah, we want this transfer function. So h of s equals y of s over x of s, which is the output over the input in terms of Laplace variables. And the Laplace variables are really helpful for circuit analysis. They can capture frequency and phase response, and it can do things like integration and derivation. It captures that. So very good for frequency response. You could go through and do these all by hand. I actually started to write out the equations and realized it was just going to get really messy. Like, these are long equations, even though there's only a few elements, but it's there's a better way sometimes. So you can see we can assign the nodes. We have every node here, like every wire between components is now gone to a different color. And I should also mention I did break up the this potentiometer into two resistors, the T times RT and 1 minus T times RT, with the idea of the variables T, B, and M just representing our treble, bass, and mid, sort of our displacement on the potentiometer, like how far we've turned it, so that you can sort of break up the resistors into two. Since these ones were voltage variable resistors anyways, with the wiper tied to one leg, you don't have to break it up into two, but you should still multiply it. So we can click resolve in here, and it's this is free software, by the way, for Linux, Mac, and Windows, but it is a little bit janky. So it doesn't really matter in our case if we take the result or the raw, but you just want to copy all of the numerator of the transfer function. And I found it easiest to put it into something like Sublime Text Editor. So that's our numerator, and let's get our denominator. This is almost the most painful part, just getting these sorted out. Okay, that's all we need this for. You can actually do the plots of frequency domain as well in here, but we won't worry about that for now. So this looks like a lot, and it is, but I found there's some tricks to sort of make this a little tidier. So first of all, use find and replace quite extensively. Make sure you're set to current file if you're like me and you have a bunch of tabs open. Those were my attempts figuring it out earlier. So I just want to clean this up. So for instance, if I have sort of the space between variables, like a space, asterisk, space, I really just want the asterisk there. So find and replace all. There's a whole bunch of them. Yes, we want that. Things like the parentheses having a space. I just want a normal parentheses. Same thing on the other direction. And the V1 in the transfer function, that's the voltage. Yeah, it's not really a true transfer function that it gave us, because the V1 should actually be taken out. This is our output, and then the V1 is this voltage source. But the V1 should actually be removed as part of the transfer function. We just sort of, that's our input. That's not the response. So to remove it, and it's only going to be on the numerator, but you can see it's in every term here once. So remove it, we just V1 and nothing in the replace field. Actually, I think it's always going to be multiplied by something, so I'm just going to remove that as well, the asterisks. So how are we looking? I think that's pretty good. Depending on how you set up your variables on the in this program, you might have to change the name of some things, but if you can name them whatever you want. So because I named this already what I want it to be, then it's already in that term. But otherwise you might have to change some names in here. So the next thing is, and going back to our presentation, you can see we have in the transfer function, the B coefficients are matched to a Laplace variable of varying powers, and the A are the same but on the denominator, and then A itself has no Laplace variable. So that's already the form we have in here. We just have to separate it out. So like B3 will be where S to the 3 is on the numerator side. So we can see, here it is. So this whole thing is B3. So let's just start to separate this out. We can delete this and just say B3 equals that, and let's add our semicolon for later. This whole thing is B2. So B2 equals, and this is B1. Add our semicolons here as well before we forget. And now on the denominator, it's the same idea. So yeah, so here is A0, the one without the Laplace variable. One handy thing if you're looking for these is, okay, this is going to be our A1. So we can just click on that bracket and we can see it's up here. So A1 goes way up here this time. I think A2 is the longest, and then the final one is A3. Just gonna check that I have brackets on all of that, or semicolons. Okay, perfect. So that's our variables in terms of continuous time domain, so Laplace. So what do we do with them? If we go back to our PowerPoint, this is what we just did, but for a different circuit. A little bit different circuit. That's for the basement again. So here we go. Bilinear transform of a third order system. And we already read here, this is the the transposed direct form II, which is very important. So it's pretty simple. We have new sets of variables now. Now these are capital BO, capital B1 or B0, B1, B2, B3. And you can see there's these Z to the -2, Z to the -3. That just represents single sample delays. So Z to the -3 is a 3 sample delay. Z to the -2 is a 2-second delay. But we don't actually have to do the bilinear transform. We can just substitute with these variables, which I already wrote out before, so I'm not going to do it again, but you just sort of copy this into our code. So there is one more sort of detail. You can see there's C's, C squared, C cubed in all of these transformations. So one thing with the bilinear transform is that it does depend on the sample rate. And in our application, the sample rate could be changing. So this sort of does some warping and also sort of frequency scaling for the various sample rates. This Karma website, you can see it's part of Stanford, but this is they have some of the best sort of reference material for digital signal processing. So if you look at their page on bilinear transform, this is also the same guys who wrote that paper. So we're kind of being consistent with the information and the notation and everything. If you look, this is how the bilinear transform actually works. You want to change S, the Laplace variable, to Z's. You can substitute S with this term, and you can see here is the C, and the C, what did they say where it is? Down here. Typical choice of C is 2 over the sampling period, or 2 times the sampling frequency. So that's what we'll be using, 2 times FS, which is the sample rate, and very easy to get in Max. So I won't go through the whole implementation, but I will sort of show you how I set things up. And hopefully the video doesn't crash. So I have a patch here. I'm taking my sub patch here. I'm taking my variables, doing some scaling. This is to just add the exponential curves that you'd see sort of here. These potentiometers, these 2 are log pots, and the mid frequency is linear. So we do want some curve, and that would become apparent later if you don't do it, just based on how they're performing. But I just have some sends. I'm receiving them, and then I'm just preparing the message with the prepend statements so that I can use those as input parameters. One thing that's worth noting, and this sort of drove me crazy trying to figure it out, but the treble parameter in this equation actually only works between the range of 0.5 and 1. So I actually scaled it here, and it's that's the one that's backwards to what you'd expect. So I flipped around the order of the 1 and the 0.5, and then added a curve of 2.5 and a curve of 2.2 to encapsulate that log plot behavior. So the meat and the potatoes of this patch is in this gen, and note this is gen without the tilde. This is the message version of gen, not this signal version. And I did this in gen just because it's a lot easier to write order equations. So here we're receiving our input parameters. I originally just had this receiving T, M, and B. I don't know why it wasn't working, but it wasn't. It was just populating a bunch of errors and format mismatches. So I changed the names here to bass, mid, and treb, and then actually changed it again here, which is not the most efficient thing to do, but it sort of saves some time. And then of course in the code it's as we prepared in Sublime. So this section is what we just did up here. That's the same. Oh, sorry, I did skip a step here. I originally had, in my gen code, I had a section with a bunch of parameters. Oh, I think Max has been crashing a lot with this gen code. Yeah, I did have a section here where I had all the capacitor and resistor values, and I do like that because it's easy to tweak things and change them, but it just was not stable. So there's another method. I think it was sort of this A2 that overwhelmed the processing in Max and Gen. So we can sort of apply some values to this, and what I used is Octave, which is sort of the free open source MATLAB alternative. So it is a little tricky to get the symbolic libraries installed. They switched over to using the Python SymPy library, spelled like this, SymPy. And it's at least on my older computer, it's a little bit difficult to get this working properly. It sort of just comes down to installing it in the right place and then pointing to that installation and the right interpreter, and then it should work, which is what I'm doing up here. So I declared symbolic variables for T, M, and B, the treble, mid, and bass, and remember this is the displacement of the potentiometer, so sort of how far we're turning it in, I guess you'd say in the clockwise direction. And I have some expressions here. These ones have an underscore just to differentiate them. But it's those expressions we just made. And one thing we can do in Octave and MATLAB is use this VPA function now. And that just substitutes the values we've assigned. So it says for this one, for the b_3 function, we want to well, first of all, we've assigned the values here for the functions, and then we have mixed symbolic variables. The VPA prints the function in a decimal form instead of fractions. So I've already ran this. It takes a little bit of time, and you might see some error messages, which is why I cleared them out before looking at my returns. But you'll get something like this afterwards. So this is, you can see there's 8 decimals of precision for each number, which I think is probably enough for what we're doing here. And then we have, return with the component values substituted in, and still have our symbolic variables here for t, m, and b. So you can see there's all these warnings up here from mixing floating point and symbolic expressions together, but it works still. So just be I guess aware that it might not in all cases. So I'm going to copy this back into Sublime. I'll start a new file. And we just have to do the same thing again, clean this up a little bit. So starting with this sim, let's take that out for all of them with a space, and we just want to replace it with nothing. This one doesn't have the space, so it didn't take it out. These are not an asterisk, they're sort of like a dot product, but that's not gonna work for code blocks in Max. So we'll have to replace that with an asterisk. Looks like there's no space already, so that's good. Replace. Yeah, there's a whole bunch of them. I don't know if this is a big deal, but on some of the expressions, if it's a negative, I know it's okay, but some of them have a positive, like e plus a number, and I don't know if Max likes that or not, so I just removed it, just the positive sign. There's only 7 of them, but just for peace of mind, because I know this works. And then, we just have to add our semicolons. The spacing on this one's a little messed up. There we go. That's only 1 space. Oh, maybe it's 2. Shouldn't matter, but yeah. So something like that, and that sort of prepares it. And then this is what you can dump into the code blocks expressions. That's basically what I have here. So we do have to assign a value to C, which is just 2 times the frequency, sample frequency. And then this is those bilinear transform variables and our outputs. And one thing to note, it's not that clear, but if you sort of have to do some reading to see this, but on their form, so they have an A0 and a B0, and you can, I guess you can leave it in this term, but the direct form equation has the B0 and not an A0, because it's going back this way. Like, it doesn't really make sense to have the A0 term. So we have to basically normalize this, which just means we're dividing all of these variables by A0, and then A0 becomes 1, and then there's no gain here on this line, so that is 1, so that works. I think that's just about it. So that's the code. We have our outputs, Um, and these are all getting sent to this structure. This is in the signal version of Gen, and I'm sending all those parameters, and I have that direct form II transformed or transposed structure here, and that pretty much gets you the Fender Tonestack reverb. So I hope that's useful if anyone else is kind of looking into this stuff as well. I know it took me a lot of digging to find out what I had to do here, but once I realized I could do this sort of automated workflow between Octave, Sublime, and I always forget the name of this program, Q SAPAC NG. Once you realize what to do, it's not actually that much work. So you could arbitrarily choose other linear circuits and do the same analysis with them, and yeah, potentially like a Pultec might be a little bit extreme because the variables are already getting long for this, but definitely any third order system I think is manageable. Higher order than that might be a little excessive. You do see, I guess, more of a shift from this IIR filter, which is what this is, infinite impulse response with a bilinear transform. You see sort of a shift away from this for the white box modeling, more towards wave digital filters, and I'm very interested in taking a closer look at wave digital filters, but for now, I think for a circuit like this is still a good approach to modeling it. So stay tuned. I will release the amp plugin once I have, I guess, the non-linear elements tackled. So that's the tube simulations and transformer simulations. So once I have that, I'll put it up on my Ko-fi page. But I hope this is informative for anyone who's interested in this kind of DSP work for simple analog modeling. Thanks. Have a good day.